Namaskar. Today I will discuss the Routh procedure for Hamiltonian formulations. The presence of cyclic coordinate in the Lagrangian is not much propagable because even if the coordinate qj does not appear in L, the corresponding generalized coordinate qj generally does, so that one has to deal the problem with all variables and the system has n degrees of freedom. However, if Aj is cyclic, Qj is cyclic in the Hamiltonian, then Pj is constant, and then one has to deal with the problems involving only 2n-2 variable, that is only n-1 degrees of freedom. Hence, Hamiltonian procedure is especially adapted to the problems involving cyclic coordinate. The advantage of Hamiltonian formulations is handling with cyclic coordinate is utilized by Rouths procedure and devised a method by combining with the Lagrangian procedure, and the method is known as Rouths procedure. The method is described in the following theorem. Describe the Rouths procedure to solve the problem involving cyclic and non-cyclic coordinate. Proof: consider system of particles involving both cyclic and non-cyclic coordinate. Let q1, q2, q3 qn, q1 q2 qn are cyclic coordinate. Then a new function r known as Routhian is defined as r of q1 q2 qn, p1 p2 pn, qn plus 1 q2 plus qs plus 2 qn t is equal to summation of pj qj minus l. I is equal j is equal to 1 to yes. The Routhian r is obtained by modifying the Lagrangian L so that it has no longer a functions of the generalized velocities corresponding to the cyclic coordinate, but instead involves only its conjugate momentum. The advantage in the doing so is that Pj can then be considered one of the constant of integration, and the remaining integration involved only the non-cyclic coordinate. Now we take r is equal to r of q1 q2 qn, p1 p2 ps, q qs plus 1 qs plus 2 qn t, and find the total differential dr as dr is equal to summation of dou r by dou qj dqj plus summation of dou r by dou pj dpj plus summation of dou r by dou qj dqj plus dou r by dou t dt. Now we consider r is equal to summation of pj qj dot minus l of qj qj dot t, and find the total differential as dr is equal to pj dqj dot plus qj dot dpj minus dl. dr is equal to pj dqj dot plus qj dpj minus dou l by dou qj dqj minus dou l by dou qj dot dqj dot minus dou l by dou t dt. dh is equal to dr is equal to summation of pj dqj dot plus qj dot dpj minus dou l by dou qj dqj plus dou l by dou qj dot dou qj dqj minus dou l by dou qj dot dqj dot plus dou l by dou qj dot dqj dot minus dou l by dou t dt is equal to dr is equal to summation of qj dot dpj minus dou l by dou qj dqj minus dou l by dou qj dqj minus dou l by dou qj dot dqj dot minus dou l by dou t dt. Now equating the corresponding coefficient on both the sides of the equation 2 and 3, we obtain dou r by dou pj is equal to qj dot j is equal to 1 2 3 dot dot dou r by dou qj is equal to minus dou l by dou qj is equal to minus pj dot dou r by dou qj is equal to minus dou l by dou qj is equal to minus pj dot, and dou r by dou qj dot is equal to minus dou l by dou qj dot is equal to minus pj. We see that for cyclic coordinate q1 q2 dot dot qs, equations 6 4 and 5 represents Hamilton's canonical equations of motion with r as the Hamiltonian, while equations 6 and 7 for the non-cyclic coordinate qj, j is equal to s plus 1 s plus 2 dot 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 n represents Hamilton's equations of motion with r as the Lagrangian function. That is, from equations 6 and 7 we obtain d by dt of dab r by dab p qj dot minus dab r by dab qj is equal to 0. Thus, by Routhsian procedure, a problem involving cyclic and non-cyclic coordinate can be solved by solving Lagrange's equation for non-cyclic coordinate with Routhian r as the Lagrangian function and solving Hamiltonian equations for the given cyclic coordinate with r as the Hamiltonian functions. In this way, the Routhian has a dual character, Hamiltonian H and Lagrangian L, and so on.